Hello, AP Chemistry 12. This is Mr. Chan. And today what I wanted to do was give you an introduction to the AP rate laws. Okay. Now, when you take a look at this, hopefully you have the notes. It says we call for a given reaction. The rate changes with a change in concentration. Now, this goes back to when we talked about reaction kinetics. Okay. Remember here, we talked about the higher the concentration, the faster the rate. The lower the concentration, the lower the rate. So there must be some sort of correlation between concentration and the rate. Okay? Because of this relationship, one can express this relationship as the rate law. So one can calculate the rate using two forms. Now, the rate of something could be the change in concentration over change in time. And this is what we focused on in Chemistry 12. Okay? In Chem 12. Or we can now calculate the rate using the concentrations. Okay, so in this particular case, to calculate the rate, we take K, which we'll explain what that is, times the concentration of A, which would be a reactant, raised to the power of some number, and concentration B raised to some power. So this is what we would call, this is what we're going to focus on in the AP Chem 12, in AP Chem. Now, what are the definitions? So K is the proportionality constant or rate constant and is unique for a particular equation. In other words, it doesn't change. Depending on the type of reaction and the nature of reactants, okay, it is unique for every individual reaction. The exponents m and n indicate how sensitive the rate change is to changes in A and B. If m is equal to 1 and A is doubled, the rate is usually doubled. If m is equal to 2 and A is doubled, the rate increases by a factor of 4, exponentially, an exponential relationship. When m is 0, the rate is independent of A. And if m is negative, that means the rate decreases as the concentration of A increases. What we call an inverse relationship. What I will do is later on, I will give you an example of what I mean in terms of independent and doubles and so on. Okay? Now, the values of the exponents m and n determine the reaction order of the different reactants, and the sum of the exponents defines the overall reaction order. Okay? And the values of the exponents are determined experimentally and cannot be determined from stoichiometry of the reaction. Now, let me give you an example here of rate is equal to K A squared, B is equal to 0. So what does that mean? So in this case, here, the rate of the reaction is independent of B, because of the 0 exponent. And here, the rate of reaction is exponentially dependent on A. Because of the square, and the overall reaction order is 2. Where did I get the 2 from? 2 plus 0. okay, from the exponent on A and the 0 on B. Okay, so the units of the rate constant depend on the overall reaction order of the rate law. So for example, let's say rate is equal to Ka squared. Now, remember rate, let's say, is in molarities per second, is equal to K, and then I have molarity squared. So what would happen is it would be K would be equal to molarity per second all over molarity squared. Okay. And then what you would have is 1 over molarity times second. Or we could say it is molarity minus 1 times second minus 1. So this unit is dependent on the rate, on what type of order the rate is. Okay? To determine rate laws, one uses observations of the effect, observes the effect of changing the initial concentrations on the initial rate of the reaction. So what we're looking at is how fast the reaction is right at the very start. And it is important to recognize that the rate of a reaction depends on the concentration, but the rate constant does not. Remember I said the rate constant is dependent on the nature of reactants or the type of reaction. Okay, how fast the reaction proceeds depends on the concentration, but the rate constant is dependent on the type of reaction it is and what type of reactants and the nature of reactants there are. All right, now what I want to do is I want to go over one example that would be typical of an example that's given to you. Oopsie. Okay. It says the initial rate of reaction A plus B was measured for several different starting concentrations of A and B with the results given. So let's say we have 3 different experiments, all with different concentrations, and what you get is an initial rate. Now, using the data, determine the rate law of the reaction, the magnitude of the rate constant with units, and the rate of the reaction when you have specific concentrations. Now, I've already written down here that the rate law is rate is equal to K times the concentration of A to the power of M, B to the power of N. Now, the reason why there's only A and B is because we have 2 reactants. If there was 3, 4, 5 reactants, then the rate would be dependent on each of the reactants multiplied together, each raised to the power of their, to the exponents. Now, what I'm going to do is I'm going to go through a mathematical process of solving this. And afterwards, what I will do is talk about how you can do it verbally. All right, so I'm going to give you both methods just to sort of cover the bases here. So for step number A, how would we determine the rate law? So what we would do is we would choose 2 experiments. Okay, so in this case, I'm going to choose experiment number 1 and 2. Now, why do I choose numbers 1 and 2 is because you notice the concentration of A remains constant while B is the one that changes. Okay, I could also choose numbers 1 and 3. All right, but notice I would not want to choose experiment 2 and 3 to compare because notice not only does the B concentration change, but the A concentration changes as well. So if I did that, so let's say if I had rate of B all over rate of A, that is equal to K concentration of A to the power of M, B to the power of N, all over K concentration of A to the power of M, B to the power of N. Now, so if we look at the rate, so for B, it was, so I'm going to draw a dot here, so just to see the separation. So I have 4.0 times 10 to the negative 5 is equal to K, oopsie, 0.1 to the power of M over 0.2 to the power of N, all over 4.0 times 10 to the negative 5. Well, let me erase this here. It's equal, K, 0.1 raised to the power of M, 0.2 raised to the power of, oopsie, here, 1. Okay, now what you will notice is that I can cancel out the rate constants because they're the same, it's the same reaction. I can cancel this out. So what I have left is I have 1 is equal to 0.2 divided by 0.1 raised to the power of N. So here, 1 is equal to 2 to the power of N. So going back to your exponents, what is 2? What is 2 to the power of N gives you 1. So therefore, N would be equal to 0. Okay? And that's what I mean by N equals 0. The rate is independent of the concentration. So now what you can do is you can find M. So what is M equal to? And again, in this particular case, if I were to solve for M, or the exponent for a concentration of A, I would probably choose experiment 1 and experiment 3. And what you will find is that M will be power of 2. So therefore, the rate law is equal to K concentration of A to the power of 2, B to the power of 0. Okay? You can do that. Now, some of you might not like the mathematics, so some of you might be able to verbally express it. So let's look at experiment 1 and 2 again. So you could say, hey, the concentration of B had doubled, and notice the rate did not change. So therefore, the rate must have been independent of B, so B must have been the order of 0, right here. Okay. And then if you take a look at 1 versus 3, notice the concentration doubled, but notice the rate went up by a factor of 4. So there's an exponential growth. So since it's exponential growth, M must have been 2. Okay, so that's how I get the K is equal, rate is equal to K A squared B to the 0. All right, so there's 2 different ways to approach it. You can look at it by breaking it down into individual calculations, or you can verbally express it. Now, the overall order is equal to 2. 2 plus 0. Okay, so that is part A. Now, you might say, well, what about, whoopsie, what about part B? Okay, let me see here. So part B, it says, calculate the magnitude of the rate constant with units. So for question number B, is what we could do is take one experiment and plug in. Okay. So what I'm going to do is maybe, just for simplicity's sake, I'm going to take experiment number 1. Okay. So what I have is I have my rate is equal to K concentration of A squared B to the power of 0. This would be 4.0 times 10 to negative 5 molarities per second is equal to K 0.100 molarity all squared. And solving it, I get K is equal to 4.00 times 10 to negative 3 molarity minus 1, whoopsie, or molarity per second. Okay. Now, some of you might say, Mr. Chan, do we have to write the B to the power of 0? No, you don't have to because it's kind of redundant. Okay. And then the last one would be calculate the rate of the reaction when A is equal to 0.05 and B is equal to 0.1. So for C, how would we answer this question? Okay, so C, we just take the number, rate is equal to K concentration of A squared, concentration of B. So we just plug in the numbers. 4.00 times 10 to negative 3. Oops, this is 0. Per molarity second times 0.05 molarity all squared. And if I do that, 4e negative 3 times 0.05 all squared, that would give me 1.0 times 10 to negative 5 molarity per second. Okay. Now, hopefully that is pretty straightforward. Okay, in regards to talking about rate law. So rate law is just another way of calculating the rate of a reaction based solely on the concentration, just looking at the concentration. Again, back in chemistry 12, we calculated the rate by calculating something over time, like hopefully what you did in your lab. But now for rate laws is we're looking at the rate solely by just looking at the calculations. All right, ladies and gentlemen, so that is an introduction to rate laws. What I will be doing is giving you the readings and the homework I'll email you the homework and the reading. And that is it for today. Have a good day. Bye-bye.